This video explain example for finding the deflection in the cantilever beam. Deflection at, let's say, point B. We have a cantilever beam. Let's say this is point B and point A, and we have UDL load of W kilonewton per meter. So we have W kilonewton per meter, and it has a length of L. So we need to find these deflections at point B. So that's the questions, and we need to use the virtual work method to find this deflection. So we have a equation to find the let's say delta B, integration 0 to L small m capital M over EI and dx. So that's the equations that we need to solve. Now we need to find small m and capital M. Now this small m due to the virtual load, and this capital M due to the real loading. So we always going to follow 4 steps, where we're going to do the virtual systems first, and then we're going to find the small m. We find the small m, which is the internal moment to the virtual. Now this is the internal moment due to the virtual loading, and then we're going to find the capital M, which is also internal moment due to the real loading, and this is let's say virtual loading. Now fourth one, we're going to apply this delta B to find these equations. Now here we like to find those things. So if you have this beam, then first we're going to draw the virtual beam system. So in that virtual beam system, it's very simple. We just remove all the loadings from the beam, and we just going to put one virtual load where you want to find the deflection. Let's say 1 kilonewton is the virtual load at length L. So the main aim of this virtual work method, that we need to apply this virtual load where we like to find the deflection. Now based on this virtual work, if you make the cut here, then if I draw these portions here, let's say this is 1 kilonewton virtual load, and at a distance, let's say at a distance of x from here, I would say that I will have a, let's say, this small m, and I have shear force and axial force. So if I want to find this small m and take the moment at this particular point, let's say sum of the moment at point cut equal to 0, anti-clockwise is positive, this will create. So we take the moment at this cut. So this 1 kilonewton create the negative, and this distance is x, so minus 1x, and this moment is minus m equal to 0, so minus m equal to 1x positive, so small m equal to minus x. So this is the first that we found this second step. Now the third steps, we need to analyze these structures for real loading, which is W, and it has a length of L. So again we're going to make a cut here at a distance of x, and where we make the cuts, we can draw the free body diagram here with this W, and thus distance is x, and where we make the cut, we will have a axial internal force, shear axial force, and we have moment. Now if I simplify this one, I would have this Wx, and this distance is x by 2, and that's the cut, and let's put only m. So if I take the moment at this point where we make the cut, and anti-clockwise is positive, then this create minus Wx times the distance is x by 2, and this moment is also minus m equal to 0. So minus m is equal to positive Wx square on 2, so capital M equal to minus Wx square on 2. So now we found the capital M. Now if I want to find the deflection, step number 4, deflection equal to integration 0 to m internal moment due to virtual load, internal moment due to the real loading over EI and dx. Now in this case we would have substitute the value 0 to L. Small m we calculated minus x, so substitute small m minus x. Capital M we just found wx square on 2, so minus wx square on 2 over EI dx. 0 to L, minus minus positive, wx cube on 2 EI dx. Now we take the constant out, w on 2 EI, 0 to L, x cube dx. Now in this case we can have a x to the power 4 on 4, 0 to L, which is w on 2 EI, L to the power 4 on 4 minus 0 to the power 4 on 4, which is w on 2 EI, give you L to the power 4 over 4 minus 0, so it would be WL to the power 4 on 8 EI. So that is the deflection at point B using the virtual work method. Thank you very much.